Well, hello everyone. Thank you for being here. I'm here to talk about Newton a little bit. And there's a thing with my name, which is way too long. It's Maria Evangelina Ferreira. You can just call me Eva, Iva, or Efa, because it's too complicated for non-Spanish speaking people to pronounce Evangelina. In fact, I'm not usually called like that, only my mother when she's mad at me. So Eva is okay, Eva, Efa, don't worry. As they say, I'm a web designer and I mostly teach at university. And I do some web marketing stuff like Facebook and AdWords campaigns. In case you wonder, this talk is about timing functions that hopefully will be useful to you not only in web design, but also in any kind of animation you make, like stop motions or an animated movie. These are the available timing functions in CSS. We got steps, linear, is in, is out, and the Bézier Curve. I reorganized this and created two groups, which are steps and all the rest. Now, steps is way too different to the others. So first of all, we look at the steps, and then we look at all the Bézier Curves with physics. Here's a little itinerary. First of all, we talk about animation, how does frames work, rhythm, and keyframes. Then about the steps, and then about physics. There will be a little bit of math in there, but not many, I promise. So after all, you get lunch. Well, let's begin talking about animation. Animation is a time-based form of art. This means we get movement through time. And in this case, we work with frames. Working with frames at the beginning can be a little bit confusing. Every frame is part of an animation. We get a 10 seconds animation and we divide it in parts. And each part is a new frame. For example, we got in here 8 frames, and each frame lasts the same quantity of seconds. And then we also got keyframes, which are the most important parts of the animation, where we provide the major changes, like we go from this color to the other. So in this case, we got this, which is pretty boring. But the important thing is that we have no acceleration. We have a linear easing. And we can check that because we have these middle frames with the same width. On this case, we have the same animation, but the inside frames are different. They have the same duration as this one. That means if this one lasts 1 second, this one does 1 second as well. But it will cover more distance than this one here, and this one, which is smaller, will cover less distance in the same quantity of time than this one. So we get an acceleration that we didn't have before. In here, the frames are smaller. That means that they are slower. And in here, they are bigger, so the animation goes faster. So that disposal of middle frames indicates the rhythm of the animation, and it's what we know as timing functions. In CSS, we got the keyframes property. First of all, we must create the animation. We provide only the keyframes, and then we apply it to the element, indicating the duration, the iteration count, how many times we want it to repeat. Direction, field mode, it means what happens when this animation ends. And the play states, whether paused or running. And then, of course, a timing function. For example, we got this animation called name, and we got 2 keyframes, from and to. In this case, we are simply changing colors. Now, here's the example of course, Harry Potter. We got Harry Potter's invisibility cloak, and we want to make it invisible. So the animation is called invisible, and it goes from opacity 1 to opacity 0. Now, we apply it like this to cloak, invisible, 2 seconds. So we can play it infinite, which isn't really what we wanted, or we can play it only once and tell it to stay in the last keyframe. That happens when we apply the field mode, in this case, forwards. So the animation, when it finishes, goes back to the last keyframes, which is 2 opacity 0. The other hand, or the other side of forwards, is backwards, which stays in the first keyframe. That's why it goes back to opacity 1. So besides that, we can add many more keyframes, as many as we want, with percentages, like here. And again, we can play with Harry Potter going to a party. Now, his cloak will change. In this case, it will change colors, because it's magical and all that. So we have many keyframes from and to. Actually, from and to can be used in percentages as well, like 0% and 100 here, and it will work the same way. 100, there. So we got Harry Potter going to a party, of course. He got shiny and color-changing clothes, and you can make it faster or slower, however you want, and usually infinite or less repeats. So those are the basics of animation, in case you weren't familiar with it. Now let's go to timing functions. So we said we have steps and the rest. Let's take a look at the steps first, because it is the most different of all. Now the steps function divides the animation. In this case, we got this green thing that turns around forever. We got a linear easing, that means it has no acceleration. The default option is ease. That means that it goes like this, but we want to apply steps. So steps is another timing function that requires a number between parentheses. The number will be the quantity of frames this animation will be divided. For example, 10. And what we see here is the whole animation divided in 10. If this number is bigger, then we get a more smoother animation, and if this number is smaller, we get a less smooth animation. Now, we can apply this to web design and to use it in some field that you might be familiar with. It's called chronophotography, which were the beginnings of animations back in the 19th century. So, two animation pioneers were Jules Marey and Eadweard Muybride. That Jules Marey is known for researching body motion, and he used to take these kind of pictures where he had people dressed in white, running and jumping in a black background. And what's interesting about this is that he created this idea of frames, of dividing a movement in different parts. He took a lot of pictures, in this case of birds as well. And then came Eadweard Muybride, who is known for the steps function and the GIF animations, even though he was like in 1903, something like that. So his most famous photograph is this one. And this picture has a story. A horse rider wanted to know if his horse didn't touch the ground at any time during the race. So he hired this guy to take a lot of pictures of the horse. And they checked that, of course, the horse didn't touch the ground at some part of the ride. And the rider was so happy that he hired this guy to take a lot of pictures a day. He took like 1,000 pictures a day, and he discovered that if he put all these images together, one before the other, he got this, which is what we nowadays know as a GIF animations, and were the basics of an animation and keyframes. And 1,000 pictures a day of cat, dogs, everything he could think of. And then we got our example. How do we apply this to web design with the steps function? In this case, we got images of a kangaroo jumping. We have 12 images. And first, we should put all those images together in one. It's one image with 5,000 pixels wide, 300 pixels high. And each single image measures 450, 300. So that's most important to make this work. Then we get the example where we got the animation hola from and to, and as you can see, we get the element with a background image, which is the whole long 5,000 pixels image, and a little window of 550, 300, which is only one image, so we get to see only one, only the first. And the animation will be applied to the background position of this image. It will go from 0, 0, which is the default position, to 5,000 pixels, 0. Okay? It won't move up and down, it will only move from right to left. So we can apply this over here, animation, hola, 2 seconds. Now, if we play it infinite, we check that this is not what we wanted. This doesn't really look like a kangaroo jumping. So, first of all, let's really check what's going on. The background is moving, okay? It's going through from 0 to 5,000. Now, what we should do is divide this animation in parts with steps, and the number of parts will be equal to the quantity of frames we got. In this case, we got 12 little pictures. So this doesn't really look real yet. It looks like a little fake. Besides, it's a draw and not a real kangaroo. And so that is because we have 12 frames in 2 seconds, and our minds need at least 10 frames per second to make it look real. So we should have at least a duration of 1 second to make it look smoother and more real, because our mind needs that. If we make it faster, then it looks horrible. Let's look at the kangaroos on drugs. So if you don't have enough keyframes, try to or draw more kangaroos, or simply put 1 second. So yeah, at least 10 frames per second to the mind to be able to catch the animation. Now, timing functions, especially steps, I always see them in animation and not in transitions, but actually the timing functions belong in the transitions working draft, so they can totally be used in transitions as well. So the very same example with a hover, we change again the background position to 5,000 pixels, 0. And we apply the transition over here, which is all to 1 second. Now, it looks like this again, so we must apply the steps function, and it will be 12 keyframes, because we got 12 over here. Wait. No. So it works on hover as well, because steps is a timing function, and it works in hover, and it's a transition as well. So, going over, why should I use steps and not a GIF? First of all, I get more colors, I get a better way to handle opacity. GIF opacity is only 0 or 1, it doesn't have anything in the middle. Sorry. We get better gradients as well. All in all, we get better quality. But we have to put the images together, and if we have like 2,000 images, that can be a pain in the ass. But well, usually we have like 10, 20, not 200. Well, what about then the rest? Besides the steps, we got all the Bézier curve, and here we got the physics. So the Bézier curve has some predefined functions, and then we got the whole world of the curve. So it usually progresses over time. You might know something like this. It's by Leah Barrow's website, cubicbezier.com. We will take a look at this through physics, okay? So, to begin with, we'll be talking about physics of motion. We won't be talking about thermodynamics or something more complicated. Only a few basic concepts from Galileo and Newton. Now, those are speed, acceleration, gravity, acceleration, and free fall. First of all, the speed is the rate of change in an object's position in which it covers distance. It's what we usually know as 20 kilometers per hour, 12 miles per hour, or meters per second. It's always length divided by time. Now, there's totally invented story. Let's pretend I only took one flight to get here. No. The distance from Buenos Aires to Melbourne is 11,000 kilometers, and Boeings can fly up to 950. That means the flight should have taken less than 12 hours, but it took like 14. So the speed should have been 790 kilometers, because we are actually looking always at averages. The plane doesn't go all the time in 950. It goes from 0 to 900 to 800. It goes up and down, and that's the average. So that takes us to acceleration, how an object goes from 0 to 950. And in this case, again, Harry Potter, if this car goes from King's Cross to Hogwarts in 4 seconds, and its speed goes from 0 to 350 meters per second, then what is its acceleration? Well, we have this math to get to know it, which is change in speed divided time interval. If we go from 0 to 10 meters per second, then the change is 10 meters per second in 1 second. We get 10 meters per second square as our acceleration. In the previous example of the car, we got 350 meters per second in 4 seconds, so the acceleration is 87.5 meters per second square. Now, this takes us to gravity. Gravity and free fall. Now, we know that every time something drops, it falls down because it's attracted by gravity. Now, gravity of Earth is known as G, and it's 10 meters per second squared. That means that every second it falls, its acceleration will be 10 meters per second. So that is actually 9.80665. For the sake of our minds, we'll take 10. And so we get this table, which shows how the speed increases over time if we consider gravity acceleration. If we let something drop for 2 seconds, its speed will be 20. If we let something drop for 5, the speed will be 50. Now, this, put in a chart, will give us this. Now, we might confuse this with the linear acceleration, but we must bear in mind that in here we're talking about the speed, and in here about progress, and they are not the same thing, because we want to actually look at the distance covered, and that is the progress. So if I let something drop for 3 seconds, will it fall 30 meters? The answer is no. It will fall 45 meters because it is accelerating, so it will cover more distance. Now, this is horrible, but the thing is, to know the distance covered in gravity, we have half times g times square. Now, that math in 3 seconds will give us 45 meters, okay? You don't have to know this. And what you actually have to understand is that the speed increases all the time, and that means that the distance does as well. So, for example, if we let something drop for 5 seconds, we get 25 times 5, 125. And that's easier to understand. And we get this new chart. Now, this chart talks about distance in time, and that's what we know as progress in time. So, as you can see, it increases, okay? So, this is what we know as the ease-in cubic Bézier function. As time goes by, it goes faster. So, what about free fall? Now, we got a little story about Galileo throwing 2 things off the Pisa Tower. You might have heard of it. In this case, he threw a watermelon and a pizza. Why not? And so, he wanted to know which one was first. What do you think? Was the pizza first, the watermelon, or both at the same time? Who thinks the pizza? Lady, who wants pizza? Who thinks the watermelon? Okay, a couple of people. Don't be afraid. Who think both at the same time? Okay, quite a lot. Well, to Galileo, both things fell at the same time. But then came Newton, and he said, hey, maybe don't fall at the same time. So he thought that they needed a higher place. And this higher place was, of course, the Burj Khalifa. So So Newton went to the Burj Khalifa, and he threw, of course, a watermelon on a pizza. You can totally picture this. And actually, what happened was incredible. The watermelon was first. So this is all a lie. You can tell Newton never went to the Burj Khalifa and started throwing things. The reality is that Newton actually never researched the exact same thing as Galileo, with things falling first and last. But this takes us to another story, which is the elephant and the feather. And if an elephant and a feather fall from the same place at the same time, then the elephant will be first. And that's because we are talking about air resistance and first and second Newton's law on terminal velocity. All in all, what we want to understand is that an object free falling will accelerate, but due to air resistance, it will eventually cease to accelerate and reach a terminal velocity. Okay? And the feather will reach that velocity first because of this shape and its mass. So let's apply all these horrible stuff to one design. Again, we have this again. Remember this? We got this boring thing going from one side to the other. If we turn it 90 degrees, we can create a free fall effect. So we have this. Now, this doesn't look at all like something free falling, okay? So we must emulate free fall. And to emulate free fall, we must bear in mind the acceleration of the gravity of Earth. So we will apply the cubic Bézier easing function to this circle falling. And as you can see here, also the frames in the middle change, which are only in our mind, they are abstract, but they change as well. And with this, both elements fell at the same time, they are 2 seconds, but we can see that this one is totally different, and it gives us a real sensation of free falling, of gravity attraction, whether this one doesn't at all. To get this a little bit better, we can apply third Newton law, which is action and reaction, that basically says that for each and every action there is an equal and opposite reaction. Now, if we let something drop, even if we don't realize the floor is pushing at us, okay? We don't feel being pushed by the earth, but it does. So this ball, if it is made of rubber or something flexible, it will probably squash and stretch. So we can apply this to make this animation even more real. Here is again. And as you can see, when it touches the ground, it squashes and stretches a little bit. Now, going forward, those 5 predefined timing functions are not really enough, and they actually all are numbers, okay? So we have way more than those stuff with the whole cubic Bézier world, where we can actually talk about Bézier curves. The Bézier curves are the one that we use in Illustrator and Photoshop. Photoshop when you use path, and maybe you never knew they were called like that. And in here, they work this way because we are working with the cubic Bézier. Okay, so not only Bézier curve, but a cubic Bézier. And we will have 4 points, point 0, point 1, point 2, and point 3. Point 0 will always be in the same place, which is 0, 0, and point 3 in 1, 1. So we will tell this to go from one place to the other in a different way. And we're always talking about progress over time. So if the line is more horizontal, we are talking about a slower animation because it will cover less progress in more time. And on the other side, if the line is more horizontal, more vertical, we'll be talking about a faster animation because we got more progress in less time. And again, here, slower. So more horizontal, slower, more vertical, faster. To create these Bézier curves, we need the coordinates of point 1 and point 2. And when we get those 2 coordinates of each, we apply them to what we know as cubic Bézier. In this case, we got the linear function that goes from 0 to 1 without any acceleration. That's why there is no curve at all. It means that it will have a constant speed and it will not accelerate. In this example, coffee we get coffee bean drinking by a not really enthusiastic drinker. And it goes from 0 to 1, and it got this linear timing function which doesn't accelerate at all. Now, if we look at other kind of examples, more interesting, then we get this one, for example, which is something that goes faster at the beginning and then slows down. Here are the numbers, and we apply it again to coffee. So we get a more enthusiastic coffee drinker. And as you can see, it goes faster at the beginning and slower at the end. You can change the speed, and it will have the same acceleration because it's relative to the acceleration. And you can make it longer, and it will still have the same acceleration, going faster at the beginning and slower at the end. Now, there are two rules to play a little bit more with the cubic Bézier. First one is that both x values must be between 0 and 1. And the other one is that both y values can be out of range, can be more than 1, and also be negative. And with this, we can create other examples. For example, one value out of range. That's when we create a bouncing effect. So here we got it. It will go faster, and it will go over the number 1. That means it will go over its destination, which is 1, and then it will go back. And this is our bouncing. Here is our value out of range, which is y2 here. So if we apply it to something simple, we can see this bouncing and then coming back to its destination, which is here. Now, this can be applied to any kind of elements and any kind of property, not only width and height. So for example, we can apply it to a transform and even a color, and the color will bounce as well. So as you can see, when we hover over it, and it goes bigger past its destination, and then it goes back. Okay? And the same when we don't hover over it anymore, okay? Because it's a transition. And we can make this more extreme with 2. And what you can see here, I'm not sure if you can see it, yeah, the color also bounces, okay? So the color goes brighter, and then it goes back to its original, which is green. So these timing functions that bounce and go back and forth can be applied not only to width and height and to positions, but also to colors, because colors can bounce as well. It goes brighter, and then it goes back. Now, what if we have two values out of range? Well, one possibility is this, where we get also bounce, but as we can see, it will be faster and more like strict. So as you can see, it kind of hits this part. What if we have negative values? Negative values are interesting because we go back before going forth. For example, here. We go before the progression time. We can always go before negative in the y, not in the x-axis, because we cannot really go back in time, like in reality. So it will always be negative in the progress. So it will be negative in the progress, and then it will go back to 1, 1, which is the destination. And we get this. So it goes back, and then it goes forth. If we wanted to go more back, then this number will be bigger, always negative. And we create whatever we want. Eventually, it will be like annoying, but it's totally okay because it's CSS. So that number, sometimes in the website cubicbezier.com, we can really push back and like -7, but we can if we bright it, so there's no problem with that. And what if we have, again, one positive value out of range and one negative? We can also create going back and then going with a bounce. And it looks like something like this, negative y and positive y. And it will bounce both ways, back and then forth. And again, we can make this more extreme, like this, with bigger numbers. And this will destroy the slides. So another example with this, way more interesting, is about bouncing in the middle of the animation. And that can be created if we change the position of the negative and the positive. In the other example, we have the negative here and the positive here. If we turn those around and we got the positive here and the negative here, then we make this bounce in the middle of the animation. Okay? So we get this bouncing element in the middle. Now, that can be, again, taken to an extreme in any way you want, like this. So, if y1 is positive and y2 is negative, then we get the bouncing in the middle. And so what we have here, first of all, try to use the steps before using GIF, because of its quality, and the file will probably look way better. And transitions are totally okay with the steps, so I have no problem using it. Apply physics whenever facing on Earth animation, so whenever you are talking about gravity and all the others, try applying physics because it will improve the animation and it will look more real. Also creates endless possibilities with cubic Bézier. You can really have fun with that. And remember, these are animation concepts, not only web. You don't have to apply them to web design. If you feel like making a stop motion, you will recognize you have accelerations and decelerations and frames as well, because it's basics of animation, actually, not only web design. And also remember that exaggerating is okay in animations, because you can get funnier and more engaging experiences. Like this, when something drops, in reality, it's like boring. But if I draw like a lot of jumping and explosions where something drops, then it will look like funnier and more engaging. Not real, but it's an animation, doesn't have to look real. This is another example. A punch never looks like that. I mean, the person will fall to the ground, really, but it is, and it does look funnier. And this one too, no one goes like this. So, thank you very much. Hope it was useful to you. And you go for lunch.